How can data science and machine learning make its way out of the lab and into all the fields all over the world?
Yeah, it's. I mean, some of the ideas that Jeremy and Thomas were talking about are kind of like the utopian dreams that, if they come true, you would really start to see a big step change in agriculture. Uh, and there are practical challenges. So when we start taking technology out in the field, things don't exactly pan out what you expected. Uh, my favorite example is, you develop a very sophisticated computer vision algorithm, and we take it out in the field, and what you have is a little bit of mud obscuring the camera. uh, Examples like these make it harder uh, to take the technology out in the field, and you have to then account for various um, scenarios like this that may interfere. Um, another example I have is, some of the modern tractors and machinery are so sophisticated. They generate so much data. We are really talking about gigabytes of data being generated every time that machine goes out in the field. And the ISO standards and the wires and the connectors in the tractor today are reaching their limit of how much data they can transfer. So the
Mm.
industry standards and bodies are having to evolve those standards to allow this much of data for precision, um, to pass through to the algorithms that are then acting on that data.
Right. So things like 5G today, emerging more and more, and then for the 6G standards, I guess, that are coming in the future, and the 7G after that, it's going to allow for more and more of this precision agriculture. I imagine, and
Yeah,
yeah, I kind of just spoke over you.
yeah. That plus also this fact that a lot of this innovation needs to probably start to operate on the edge. So when you develop these models, that
uh,
uh, transferring that volume of data from remote fields back to the cloud could possibly be a,
right.
after the fact sync, but you allow the machine to intervene right there when it is out in the field, by operating on the edge. um, and there is this combination of applying the data to decide to create a prescription or to prepare a product, and then take it out in the field. So you don't have to do all the computation out in the field, based on all the data that we have seen, either through the IoT sensors, satellite imagery, or the last time the tractor was out in the field, which collected so much data. We could create prescriptions, and those prescriptions can be sent as an instruction to the machine, which is then geocoded. For example, let's say about a herbicide application. So the machine goes out next time, and it is carrying out that prescription as applied.
Very cool. Yeah, it's interesting that I didn't even think of that. I mean, we talk about edge computation on the show pretty frequently, but for me, it was like, oh, we just need to figure out a way to get all these huge amounts of data, gigabytes today, terabytes tomorrow. Let's just get some networks and get those all back to Syngenta servers so that you can be processing. But actually, yeah, the solution you're describing makes much more sense, where we have the models working on edge devices. They can just be working there in real time. And so it's interesting now that you mentioned these huge amounts of data coming from devices like tractors, where on the one hand, we have huge amounts of data coming in, more than can possibly be sent, more than can possibly be processed. And simultaneously, we don't have nearly enough information. We're missing a lot of the information that Thomas and Jeremy would like to have in order to be able to make their best recommendations and have, real precision agriculture. So yeah, it's an interesting situation where I guess and it's the natural way that things will evolve, where the maker of the tractor is thinking, well, I can sell more sensors on this thing and the farmer will pay for them. And so then, there's more and more and more data being collected of this very specific type that isn't necessarily exactly what you need in computational agronomy to get the best out of an individual plant or get the best out of an individual farm. So yeah, so I guess there'll be all these changes. I mean, it's amazing how rapidly things change. I wonder
we can start to think about, the difference between what's perfect or what's best versus what's good enough.
Mhm.
To build upon your point that we could have the most sophisticated models that need the most precise measurements at, in near real time. But then there is also a cost associated with collecting that much data and processing it, and so on. uh, for the most part, it might be good enough if you were to take reduce the sampling rate or reduce the frequency, and so on. And I think that's one philosophy which we try to follow, is to strike a balance between, the most perfect data point, the most perfect sensor, the most granular possible, versus what's good enough for the most part.
Yeah, yeah, yeah. And so as any regular listener of the show will have heard, I'm constantly talking about large language models, open source LLMs, the way that these are dramatically transforming the field of AI. Everyone in a huge portion of the world now is aware of tools like ChatGPT in particular, and so these transformative changes happen really fast in AI in data science. But hearing all three of you describe the problems that you're tackling, it is abundantly clear to me that not just for years to come, but for decades to come, there will be problems to solve here and situations that can be optimized. Because even if Thomas, sitting in his lab, is able to come up with this outstanding model, or Jeremy knows from his computational agronomy that there's this great opportunity to be optimizing yield, it's still going to be so many years, it's going to be decades before the hardware can be out there to be collecting the relevant data in the way that you'd ideally like to have, to be able to compute on the edge or to be able to transmit those data for processing on a server. There's like, yeah, I mean, there's certain situations like I imagine in the West, there's particular situations where tractors say are able to collect a lot of data. But then when we think about farmers in the developing world who maybe just have a phone, and they might not even have that today, and relatively low bandwidth over satellites in a lot of these places. And so you can see that even if the data science and the AI progresses very rapidly today, there's still decades and decades of work to ensure that all of these advances propagate out. And then there's this really nice, AI investors love to talk about flywheel effects. You've got this flywheel effect where as more and more of those devices get out there, as we have more and more edge compute, as more and more of these algorithms are developed, as these kinds of standards that you were talking about there, Faraz, as the standards become standard, and there's better interplay between devices and models and providers, there will be this flywheel effect where more and more models can be useful, and then so more and more hardware is useful in the field, and this is just this continuous acceleration of precision agriculture. That's really exciting. So,
Yeah. And if I could just build on that, there is
yeah.
one additional factor that will happen. I mean, yes, it will take time to perfect what works in the lab and make it scalable out in the field with all the variability that comes, out in the field. Um, but there are some interesting effects which will happen. So it may not probably take decades. It will probably happen sooner. um, is a leapfrog effect. So where
Oh, right.
farmers, countries, and economies will learn from what's happening elsewhere. And I'll take a very simple example of the use of drones in agriculture. Now, the Western farmers, the developed world, went through several iterations of perfecting what a drone can do, whether it is scouting or spray application in a field. Um, but the developing countries, right, would probably get there in one single leap, because they don't need to redo all of those learning steps. Um, the same drone, which will need to come back for recharging, which is limited by its range, or the capacity of the tank, when it is flying over a 2000 hectare field in US, can quite easily in a single fly pass cover a 10 hectare field in India. So the technology which got incubated in a different market probably is going to reach its limit of applicability, but in the other markets, it's ideally suited, and that will then trigger this leapfrog, the flywheel effect that you spoke about, where you have farmers who are starting to get aware of what the drone could do for me, and you have micro entrepreneurs who are coming in to help the farmer operate the drone, and then we have the data and the products that actually leverage the availability of the drone to make an impact for the farmer.
Yeah, and
Wow.
probably to add one more of these impacts that can actually propel us by decades, right? I referred earlier to the challenge of translating what happens in an experiment to the real world, right? And the more actually our farmers are professional data workers of some sort, right? And the more data we have of what happens on the actual farm, and people are sharing this, and ideally we're sharing a lot of our data, and farmers are sharing their data in a very open data ecosystem, right? The better we can actually understand what happens on a farm, on the field, and how it relates to what happens in the experiments.